that. Yeah, so this is just posted on Archive this morning, so that's the reference number if you don't have a copy of the paper. So first off, I want to talk a little bit about where we get this idea of punctuated chirality from. And so if you're familiar with different models of evolutionary theory, there's a specific model which was proposed in the 70s by Stephen Jay Gould and Niles Eldredge about how evolution is characterized by rapid speciation on short geological timescales. So it doesn't necessarily mean it's like days, but maybe 50,000 years, which is short on geological timescales. And then in between, it's just a period of stasis where the species exists unchanged for long periods of time. And so this is pretty well supported by the fossil record, so it's definitely an interesting theory of evolution. So what we did is we kind of thought about how this type of idea might apply to the origin of Homo chirality. And you can think about chiral systems interacting with an early planetary environment, which was probably very turbulent. And what would happen in that case is that you would have short periods where the environment actually influences the chirality a lot, and then you have periods where it's not changing so much. So that's kind of what I'm going to talk about. We did large statistical studies of this, and that's what I'm going to be presenting today. So it has been shown that environmental effects can actually destroy memory of previous bias. So I'm actually going to address this by applying to the Ginsburg criterion of phase transitions in a little while. So you'll kind of see where that comes from. Oh, sorry. Okay. So we have to start with the model. So we choose a bottom-up approach where chirality came first. And so we're going to use the model of Sanders, which I'm sure you guys are all familiar with. So basically, we're going to stick to the convention of having the feedback created by the longest polymers in the system. And Ks and Ki are the rate of attachment of the same monomer on opposite.
Anzi is not familiar with this.
Okay.
So maybe you should say a few
So,
more.
okay, so sorry. So you have polymer chains grow by attachment of a monomer of the same chirality, and that has a rate coefficient 2Ks because it can attach on either end. If it's just the monomers, the rate coefficient is half that. And then if you have attachment of an opposite monomer to a growing chain, the rate is 2Ki. And what's really interesting about this model and why it bifurcates is because this chain can no longer grow on the side attached to a wrong monomer. Okay. So those chains are terminated and they're kind of taken out of the reactor pool, unless you have some dissociation.
Oh, right. And they have a factor of 2 because it can polymerize on
right,
both ends.
so we assume that it can still polymerize on the opposite end, because these chains can be pretty long. So I tend to think that this end is not going to necessarily know about what this end is doing. Chemically, I'm not sure if that's necessarily accurate. I don't know, somebody in this room might know. But
Yeah, it's probably not, right? Because in both peptides and in
they tend
nucleotides,
to polymerize on one end.
it can only polymerize on one end, yes.
Right.
And so I really wonder why Saunders actually did it this way.
I think that the idea is that he's not talking about peptides, but nucleotides.
But then
Right.
it's also not right. Because
It's not right, but
because
if you think about non-enzymatic polymerization of nucleotides, maybe you have... Anyway, they can't attach by themselves, so they can't attach by themselves on the same side. Well, it doesn't really work.
But you always polymerize on the C3 carbon, not on
Yes,
the
because it's enzymatic. But I think if you think of non-enzymatic, the process may be slow, but maybe you don't have this selection at one end if there is no catalysis.
Yeah.
I think it was the idea when he was writing that. Just
It doesn't really matter in the end.
Right.
Both are very similar, and it
Yeah,
would
that's
simplify
it. I
significantly
looked at
because
them
then you
both
would lose
numerically, and they're
you would
almost...
lose the factor of 2, and you would lose the second 2 equations.
Right.
Because I think that if you want to be exactly chemically right, you should there should be 2 different kinds of kinetic weights depending on the ends, because the ends are different.
Right.
Yes.
And then you can put one to 0 or the other if you want to. But okay, better
Yeah.
change the problem.
So, yeah, I've looked at, like, the dynamics doesn't change too much, obviously the time scales too. But, yeah.
And then you have the substrate.
So we don't actually, so we have the substrate, which is just, this is the catalytic formation of monomers from substrate, and it's dependent on the longest polymers in the system. So, right. But that's what, I think that, like, usually I wouldn't use this convention, but we're going to truncate the system to n equals 2, so it's essentially only the dimers that are providing the catalytic feedback.
Just so the source for the monomers, it's supposed to be fixed concentration or feed by a fixed flux of compounds?
Fixed concentration.
Fixed concentration.
Right. Okay. So what we do is we actually couple this, or actually we study it in space. So we make a reaction diffusion network. And so the simulations I'm going to show you in this presentation are all two-dimensional. So you can think of them as simulating like shallow pools, where life might have first evolved on the early Earth. So something maybe like this. So, and this is just the diffusion coefficient. Okay, so probably some people in this room are very
Minus, of
familiar
course,
with
right?
What?
Minus,
Right.
before.
Oh, yeah, sorry.
That's correct.
Yeah, I noticed that this morning, and then I was going to change it, and I didn't. Thank you. Yeah, so it's sorry.
Yes, correct, of course.
Right. Minus. Sorry. I did see that. Okay, so we are going to truncate the model 10 equals 2 because what we're going to do is study large statistical samples. So when you're doing numerical simulations on a large grid, you want your system to be pretty simple, and solving one equation is a lot easier than solving huge systems of equations on a lattice. So also, this is relevant because the cell reaction used dimers as catalysts, and this was the only example of an autocatalytic reaction leading to chiral purity. And so, probably Axel's very familiar with this model. So basically what we do is define symmetric and asymmetric variables. And if you do that with the model I showed previously, you can actually reduce the system to two coupled PDEs down here. So it just describes the symmetric and asymmetric evolution of the monomers. So this is a very simplified model, but it does have a lot of features of the larger model. So then what we do is the equation for S from the previous slide has a fixed point of 1, and if you actually study the dynamics of the system, it approaches that on really rapid dynamical timescales. So we set S equals to 1 for our simulations, and we end up getting an equation that looks like this, where V is the potential, as we call it in physics and other fields. And so we end up with a really pretty double L potential, which when a physicist sees a double L potential, they get really excited. So we can talk about phase transitions and stuff. So that's kind of our inspiration for wanting to study the influence of environmental effects on this model. Okay. So it's essentially an effective field theory where the order parameter is the asymmetry in monomers. So, when you study the spatial evolution of this model starting from neurosemic initial conditions, and this should actually be like a lattice average value, you find that you'll get domains forming of both chiralities, so like this would be the left-handed and this would be the right-handed region. And what happens is if both chiralities percolate the lattice, so basically they span the entire length of the lattice, they'll get stuck and the system won't evolve any further. So this presents a large problem when you're studying the spatial dynamics because there's really no way to get rid of them. So basically, dA dt equals 0, and it's at some neurosemic value because you have domains of both chiralities. So you can say, well, what happens if you have presence of some kind of bias from purity violation or something like that, possibly CPL? The pressure on the walls isn't really enough to actually move these on any dynamical timescale that's relevant for early Earth. So that's been studied actually by my advisor, and you can look at those calculations in the archive paper. So what we're trying to address is how do we solve this problem of these domains that exist and we can't get rid of.
So why did you say the average is time independent? Okay.
Right, because the domain walls get stuck.
Oh, right.
Right. When that happens, the net chirality is not changing anymore because they're essentially, like, these will straighten and
Oh,
they'll
but
just exist like that for...
But they only get stuck really in one dimension, I thought. Not
No, in 2 dimensions. You get, it's a domain wall. So in this region, A is 0. Here it's plus
Yeah.
1 and minus 1.
But they're
And because
curved.
of the energy here, you can't get rid of it.
But they're curved. The walls are curved.
Right. So this is supposed to show you that they're changing, right? So eventually, like this particular one I'm showing you here, eventually you'll get something like this.
Yes. Kind of
With straight
here.
walls,
Yeah.
right? And because this goes all the way across the
And
whole
this is
system,
stable.
it's stable. It's topologically stable.
Mhm.
Right. So they won't ever go away. So to try to solve this problem, we coupled the system to an environment, and we're motivated by evidence that stirring or turbulence can influence chirality. And also by the fact that obviously prebiotic systems interact with an environment. So we do this via stochastic spatiotemporal Langevin equation. So basically, this Z term is a white noise, and it has a 2-point correlation function such that at different points the noise isn't correlated, and the mean is 0. And so this parameter A is basically a measure of the magnitude of the external environment. And you can think of it as a pressure or change in concentration. I think intuitively it's easier to interpret it as temperature, because that's kind of familiar from Brownian motion. So basically, in that case, A squared would be proportional to the temperature. So I'm going to talk about it as the temperature for this talk, just because I think it's more intuitive. Okay, so I mentioned previously about the Ginzburg criteria for why these walls won't move due to biasing pressure. So I think I'm just going to show you a quick calculation on the board. It's pretty straightforward, but just to kind of see where that comes from. So the Ginzburg temperature, or the Ginzburg energy is usually defined as this, but you can also define it as so this delta V is from our potential, and is basically the magnitude of the potential at the at the maximum minus the potential at the 2 chiral minimums. So this is V of 0, and these are V of plus or minus 1. And then this V here is the correlation volume, so it's approximately equal to 4Z cubed. This parameter here is just the correlation length. Basically, it's the shortest distance in the system where 2 points are correlated with each other, so they know what the other is doing. So it's a pretty tiny number, right? So this is just from statistical physics. So
subscripts mean derivative, yeah?
this is actually just that telling you that this is the correlation volume.
Yeah, but V sub psi means dV by d psi, right?
No.
No?
I'm just doing that so you understand that this volume is the correlation volume. So it's a size, it's proportional to the correlation length cubed, basically. This is like you can think of this as a circle radius of the correlation length. So things in this volume are correlated with each other outside the volume, a point inside the volume.
Oh, and it's eta, it's not psi.
Oh, sorry.
Sorry, it's eta.
I always get my Greek letters confused, sorry. Okay, Eda, thank you. So that's just the simple form of statement.
Yeah.
This is just a definition from physics. So when we think about what the Ginzburg energy actually is, if you take a block of size correlation volume and it all has its, let's say it's chirally pure, so A equals plus or minus 1 inside that block. The Ginzburg energy is how much energy you would require to flip half of those to the other chirality so that A would be 0. Right, so that's what that energy is defining, and that kind of makes sense because you've got this potential barrier here, right? So you need it to go over, you need to change this much in energy and this much volume to flip it, right? So, but you can also define the same thing by taking, so this subscript again is not a derivative, it's just the number of molecules in a correlation volume. Okay? So you can think if you flip half the molecules times the energy to flip one molecule, then that should be the same value. Right? So if I equate those, then I get an energy to flip the molecule of 2 delta V V correlation over N correlation. Okay. So, okay, so that basically just comes from the two formulas. This one. Okay. So, the only thing that we're missing here then is what this correlation, what the number of molecules in a correlation volume is. So to find that, we kind of have to define what a microscopic length scale is, like what the size of a molecule is basically in this model. And so what Marcelo actually did was look at the parameters we use in the model and determine, I want to make sure I get the number right here. Okay. So if you look at combining your parameters in the model, you can define this microscopic length scale to be about Q over Ks, so minus 1/6. And if you actually look at what the rate coefficients are, this will come out in centimeters. And basically this means it's 2.1 centimeters. Okay. So we're going to just use this for purposes of illustration as our microscopic length scale. And then the correlation, number of molecules in a correlation volume would be the correlation, it's basically a ratio of the two volumes, so there would be 4 zone prime here over scribble micro. Sorry. I'm like leaning because of my leg, and I think I'm writing on a slant here. Sorry if you can't read it. So the 4's obviously cancel out. So we just get a ratio of the cubes of the two lengths defined in our system. So this is the correlation length, which you find from this equation. And actually, I'll write down what that comes out to be for you. Okay. So if you put the values you get for
well, lambda, yeah? Lambda 0.
Yeah, lambda 0. So lambda 0 is
yeah. Right, I see.
Right. So Q is the formation term for the substrate. Ks is the reaction rate for the system of attachment of monomers or polymers in the same chirality. And there's a factor 2 in there. So this is the diffusion coefficient. So we had this, actually this is Ks, I think. No, that's right, never mind. Okay. So if you actually do this out and
That's
do
the diffusion coefficient, yeah, right.
yeah, it's a diffusion coefficient because this is basically if you want to redimensionalize the length, this is the primary you would use. So basically, if x equals 1 is your shortest length on the lattice, then when you make that a dimensional parameter, actually, sorry, this is not. This is equal to square.
Yes.
Right, sorry. Okay. That makes more sense. Okay, right. So, what you end up getting for EF if you do
Now, is this an eta? That's because you're still like psi here, apparently. What do you
right.
mean? It's a correlation length.
Yeah.
And
So I'm currently
here, psi
using, this is not the same thing as this,
No,
sorry.
it's functional.
That's the white noise term, and
Sure,
this
okay.
is, I write my etas the same way as the font writes that, so, sorry. So this is a correlation length in all of this. It's a different parameter.
I will call it first of all the diffusion length.
Yeah, actually,
And the fact that it's a correlation length is maybe not exactly, it's a result perhaps, if anything.
right.
But maybe, of course, it's kind of obvious.
Yeah. I guess since I intuitively, I usually think about systems that way because in physics, when we study phase transitions, we usually talk about things in terms of correlation length, but diffusion length is also.
And that's really the width of your Riemann force.
Right.
So therefore, it's really not actually the diffusion, the correlation length. If you look at your picture
Yeah,
and you were to determine the correlation length of your actual A field,
right.
that's very different from the correlation length.
Yeah. I'll have to think about that. Interesting. Okay. So,
But did you follow this business with the energy business? No. I also didn't. So maybe it's worthwhile trying it again.
sure. Okay.
Not
So,
solely.
so is this kind of clear where this comes from? About flipping, going over the energy barrier?
Yeah, dimensionally, maybe not quite. I mean, E is.
So, okay, I think maybe where the confusion
E
is
is
that...
an energy per unit mass, right?
Right, and so,
Isn't it? I think it should be, and therefore it's strange that you have volume on the right hand side.
no, this is the total energy in correlation volume. I don't,
Maybe the energy per mole.
Maybe
the,
you're right.
the
But
difference
delta
between.
V is an energy per.
No.
Yeah, but it's the difference of the
Oh, wait,
chemist
yeah,
energy
so-
and the
so this
physicist
is-
energy.
yeah.
In chemistry, it's always per mole.
Yes, but
Maybe it's something like that.
in physics it's per mass, right? kB times T is the energy per mass.
is energy.
Is the
Yeah,
energy
kB
Yeah.
not the
Yeah,
mass?
kT
I see.
is
It's not the
energy
mass,
anyway,
it's just the
yeah.
total energy,
Yeah,
and
and
so, yeah, so,
yeah,
okay, I got
fine.
confused for a second too, but, so
Yeah.
delta V is an energy per
Okay,
unit
fine. Then it
volume.
makes sense that it's
Right, and then you
okay.
multiply times the volume, and then down there, that's just a number times the energy to flip one. So
Right, yes.
it's the number of molecules you're flipping times the energy per individual molecule.
Yeah, but isn't EB the same as delta V?
E, which one?
E little b, isn't that the same as delta
Oh,
V?
this is an F, sorry. No, because this is an energy per correlation volume, and this is an energy to flip one molecule. So there's a lot of molecules in a correlation volume, because this is like a coarse grain system. So you don't define each molecule individually. You define the chirality in blocks. So each block is describing a bunch of molecules. So this describes the potential for a block, and then this is for the individual molecules in the block. Does that make sense? Or?
F is for the block. Or EG is for the block.
EG is for the block. EF is what we're trying to find from this calculation, which is for an individual molecule in the context of this model.
And
So this is what we're trying to solve for.
and sub eta is the
Because we can figure out, because we know the smallest length scale of our system, what EG is from our potential and the size of that smallest length, and then this is kind of an ansatz of what that should also be equal to, right? Because we're saying there's got to be some energy to flip an individual molecule within that correlation volume, and so how many molecules are total in that correlation volume? If we want to flip half of them to get the chirality in that volume to 0, that would be equal to the Ginsberg energy.
so n sub eta is the number of
Molecules
in
in
the
the
volume.
correlation volume. Okay.
And how do you go
Is
about
that
that
what
out?
you're trying to work out with it?
Yes.
So what I'm
Well,
trying to
just
get,
say- and
I'm
then-
trying to come up with some kind of physical intuition of what the energy is to flip one molecule.
Yes.
Right.
And then you have on the right hand side that was in n sub eta is eta cubed over eta
Micro.
micro.
So what I'm trying to, so what
Yes.
this is saying is eta is the shortest length scale in my coarse grain model.
Mhm.
But there's actually, realistically, physically, there's a shorter length scale, which is the molecular size.
Right.
And that's what I defined as eta micro from
Yes.
the parameters of the
Okay.
model.
Yes. And this eta micro is the length scale is basically the mean free path or something. No.
Right.
The,
Yeah.
the separation of molecules. Right.
Okay, yeah.
Right.
So eta divided by eta micro cubed is the ratio of the correlation volume to the microscopic volume of basically the mean free path cubed.
But this is just a unit of the system because I think the concentration can be still higher. It's the
Right, so this is kind of, yeah, we haven't really defined what the concentrations are, but we're just,
if you mean what if you know what I mean.
I think
the concentrations are measured in units of Q over Ks,
Right.
but the actual concentration is, of course, this value times whatever the non-dimensional number is, which
Right.
can be which you have to obtain.
Right.
Okay.
So it's just kind of like we're just trying to get a rough idea of
Yes.
what the energy to flip is. So this is kind of like a back of the envelope calculation, if you want to think of it that way. It's just kind of like to give you an idea of what is physically happening in the
Okay.
simulation.
So is it then large or small?
Yeah, it's very small. So so all the energies in the system, because we're working in semi-dimensionless units, are in units of. Yeah, so yeah, you have to understand it from a theoretical physics point of view. So the first thing we do is try to get all the units out of the equations, and then putting them back in is kind of like, a big problem. So, but if you wanted to redimensionalize it, it depends on what your parameter A is, because that's what your actual input parameter for the system is. A is what you would actually measure in the laboratory. So we haven't correlated this to any experiments yet, so don't have really a value on that. But anyway, this is a pretty small number. Okay. So that may not look like an energy to you, but what's actually going to be relevant for the point of illustration here is a ratio of that energy to the environmental energy required to flip the chirality of one cell, because I want to show the relative strengths of the environmental influence A, the energy of that, with the energy to flip an individual molecule. So you can think of this as maybe the energy to flip an individual molecule as, something like from Purity violation or CPL or something. If you have like an asymmetry there, basically what it would do to the potential is you would have small tilt proportional to the asymmetry. So like if you think of weak neutral currents, say, then you have like a asymmetry parameter, G is delta E over KBT, which is about 10 to the minus 17. So you would have like a really teeny tilt in this potential here. Like one of these maybe would go up a little and one would stay where it is or go down. So that would just change the delta V by a very tiny amount. So effectively, this is about the energy to flip for most cases that we're looking at, for what could possibly be an energy difference.
If you wanted to explain this in terms of parity violation.
Right. So just to give you a physical example of what an energy difference might be between
Yes.
two chiralities, because whatever it is, it's going to be really tiny, because we haven't found it yet. So.
Okay, so you're then using from now on these physical values of 10 to the minus 17 or whatever?
No. So that's just an illustrative example. And this is an illustrative example of what, in this model, that EF is equivalent to with this potential.
Mm-hmm.
Okay. So everything is in the context of this model, but I'm not actually going to use that G. I just wanted to kind of show you that this is realistic for those kind of energy differences. Okay. So when you have this parameter A, you can actually study its effects on the dynamics of the system. And so here's one of my favorite things is our phase diagrams. So if you start from an initial condition where all your correlation volume cells have a net chirality of plus or minus 1. Right, so here we start with plus 1 for the simulation and no noise. And if you let the system evolve in the presence of this environmental influence term or noise term or temperature, the system will reach an equilibrium state where the net chirality doesn't change after a period of time. So this plot here actually shows for different values of A what the equilibrium value of the net chirality is, or the enantiomeric excess. Right? So if you have no noise, your net chirality can be 1. So you have 100% EE. Now, if you increase the noise, what happens is that your EE starts to fall, and eventually you reach a point which we call the critical point, where A equals 0 everywhere in your lattice. So basically you have a complete racemic lattice. So you start with homochiral lattice, and if it's in the presence of noise, it'll be racemized by the presence of this noise term.
Is this actually a perfect bifurcation, or a sharp one, or is it imperfect?
So, as far, I'm pretty sure it's perfect, but we haven't found the exact point yet. Actually, I think, Joel got it pretty close here. So this was a simulation that was actually done by Joel in our group. My simulations are effectively identical, but, he actually did this work.
Oh.
So he found these values here in 3D and 2D, and I think those are pretty exact. So I think it's a perfect bifurcation. And so basically what the simulation represents, I probably should have told you this at the beginning of the slide, is we set up a lattice, so it's a square lattice, and it has periodic boundary conditions. So this side is equivalent to this side and this and this. And it's 1024 squared, so it's two-dimensional. And
28, probably. 20, sorry.
So okay, it's okay. So it's a large lattice, but the spacing on the lattice is like dx is 0.2. So if you actually work out what the size would be in physical dimensions, it's about a 200 centimeter pool. So the area here is about 200 centimeters squared. Okay. So if you add this kind of a stochastic forcing, if your parameter A is larger than 1.15 in 2D, A squared actually, then the fluctuation has a sufficient energy to actually drive the system toward a racemic solution. Okay, so if you think back to what I was just talking about here with having a correlation volume cell with a homochiral distribution on it, so it's all one chirality. Effectively, to get it racemized, you're flipping half the molecules, which is what we were kind of talking about here, right? So we want to translate this to an energy so that we can compare the environmental energy to the energy to flip a single molecule. Okay. So, actually, if you actually translate this 0.65 into dimension units, you get AC squared 0.65 times the length to the 3 halves, right? So we already know the Shor's length scale, so this is the dimensions of length. So you just multiply by length to the 3 halves, and then you get the environmental energy is
0.65 comes from where this bifurcation appears.
right, exactly. So I'm trying to figure out, right.
0.82.
But it
Yeah.
looks like 8 pounds, right?
How do you calculate your error bars? To the right of the bifurcation, when the bifurcation
So it's
hasn't happened, the error bar should encompass a 0, shouldn't they?
well, they do zeros here. It's not right at the bottom. So this point, okay, so the plot's a little confusing because this is A, and this is closer to this A squared.
Yeah.
What's the difference? Ah, sorry. Oh, I see.
So that's how you get.
Yeah, sorry, I probably should have pointed that out. So zeros here, so if you draw the straight through here. And these are an ensemble average of a whole bunch of runs. So they're not just individual points, and that's where the error bars come from. Yeah, so if you take the square root of this, it's like in here. And so. Okay. So,
And the top was, that was 3D, I see. But there you say 1.15. No, sorry.
that's in
That's
2D.
in 2D.
So I put 2D up there because my simulations are actually in 2D. And so when I talk about comparing it to the magnitude of that noise term to what I did in my simulations, that's going to be the relevant value, right? So we've also looked at this in 3D, but statistically, so qualitatively you see the same results, but statistically it's just too much to do. Like we use terabyte computers and so really large CPU clusters to do some of these simulations, but for the 3D it's just too much to actually do any kind of statistical testing right now. So we stuck to 2D for this. Okay, anyway, so this is 0.65. Great. Okay. So the environmental energy to flip molecules is then about 10 to the minus 6 meters cubed. And so if you compare the two, at the critical point, so this is obviously the critical value of the environmental energy. The environmental influence is a lot stronger than the energy difference between the molecules in this model. So basically, if you have an environmental influence with strength around this value of AC, then you pretty much wash out any influence from previous biases that the molecules might have. So you basically reset the system. Okay.
So that really, environmental means thermal effects.
Right, so it can be thermal. I say thermal because I think that's easiest to understand is that like increasing or decreasing the temperature. But really we haven't specified, I mean, we're giving this as an example to show that it's an energy, but really A is not specified. So it could be a pressure, it could be a change in concentrations. It could be really like any kind of environmental influence you can imagine impacting the system. And so we would actually have to put whatever that parameter was into this model to figure out where the critical point would be.
Yes.
But it's pretty much an open parameter. So it's just some kind of noise, external influence, however you want to think about it impacting the model. Basically creating these fluctuations. Okay. So what we ended up studying were, I talked before about these systems that end up getting stuck in this semi-racemic state with these domain walls. So they're basically stuck in a nearly racemic state, so they can't change at all. So what we did is we took those kind of solutions, because those are obviously the ones that don't describe the physical world, because we obviously observe homochirality. So we took those kinds of solutions, and you can see in the EE or A term as we have it here, that those solutions get stuck, basically, is what I call it, stuck. So dAdt goes to 0, and you don't get to plus or minus 1 like you would like to, right? So what we did with those is we turned on and off the environmental influence. So if you turn on the environmental influence for an extended period of time, like here we do it for 100 seconds in the simulation, then you can see that all of these solutions that were stuck with these domain walls kind of get mixed up a little, and then they can start evolving toward homochiral states afterward. So basically it creates this kind of, it adds energy to the system so that those domain walls can be broken up. Okay. So, and then you can see here that sometimes, so these near racemates can start moving, but sometimes you'll get something that's moving in a specific direction and they get stuck again. So like this black one here, it looks like it was kind of moving toward a chiral solution, and then it got some noise, and then it got stuck again. But for the most part, the noise, at least longer-term noise, actually really affects the system. If you have short environmental influence, it doesn't really do too much to the dynamics. So that's kind of something that's really relevant in studying these systems. And so this is really what I use as my measure of the strength of the external influence, is the ratio to the critical value. So that really then, this would be your input parameter into the model, so you would be able to figure out what is the strength of the influence in terms of the critical value, of whatever you determine it to be. Okay.
Now, you would really expect that there's always a random forcing being on, of course.
Right.
But then, of course, it may
It'd
be
be
much
stronger at some other times. So if you actually run the entire simulation with a low noise the entire time, it doesn't really affect the structure of the domain walls that much. So I didn't include it in the simulations because to have a random number generator on the entire time it requires a lot of CPU hours. But it doesn't really, it won't move the walls. So I have another simulation I could show you with that. But basically, you just kind of see like little fluctuations about the values that are already there. But the domain walls can still form with really low temperatures or environmental influences occurring. So if it's really, really low. And then these are kind of relatively high values, so they're violent events that affect
Yes.
it.
Now, you were a bit careful talking about temperatures and stuff, but doesn't
Right.
that make sense? And then the question would
Right,
be...
so I think temperature, I like talking about temperature because to me that makes sense and it's kind of easy to think about,
Yes.
right?
And so what is then the A environmental value that you would expect from room temperature and the Q and K
So
values
that's where,
that you have on the board?
so that's where you would need an input parameter. So you would need to actually go into the laboratory and measure
Yeah,
the temperature at
But if
which.
you take those parameters, which perhaps are consistent...
So there's a missing, you can't actually get an A value in terms of an energy or a temperature because it's in meters cubed here, and there's not really a conversion for that until you put a parameter into the system.
Yeah, but you take the Q and K values as your measure,
Right,
Ks and Q,
yeah, no. Oh,
right?
yeah, well that comes out to be this, right? Well, this.
Or maybe you don't...
Yeah, no, because if you put those two values in here, you get this value here, but you still have the energy in terms of meters cubed, and you can't. There's not like a parameter in the model to transfer that to an energy without putting. You need.
I mean, maybe what you're missing is the mass unit. Yeah,
Right. Yeah, that is what we're.
That's what you're missing, yeah?
Yeah.
But you know that because you know how big the how heavy the molecules are.
Right. Yeah, we've been trying to figure out like a physical value for A, but there's some problems with translating it without actually doing an experiment. So really what this model requires is some experimental verification
Yeah, okay.
and then input.
Yeah.
Alright.
All right.
So what I just wanted to show you just to give you like a physical picture of what is actually going on. An actual simulation of one of these runs. So this one is going to show you this particular run here where A gets stuck in this neurosemic state, and then we turn the noise on for 100 seconds, and then you can actually see the domain walls disappear. And so this actually did start at racemic initial conditions, but this is a little bit into the evolution. I had some problems transferring this simulation onto my Mac from my PC, so I think you'll be able to get the idea. So you can see the domain walls forming. And so I let the simulation run multiple times. So this solution stays stuck unless you do this. And then you can actually see that since these are now closed domains, they actually shrink away. And you get, in this case, you'll have all R molecules, basically right-handed. So the left-handed will disappear. So that kind of gives you a physical picture of what's actually happening. Okay.
But not always, apparently. I mean, looking at your previous plot, sometimes you...
Right, so sometimes. So what we did, that's where the statistical analysis comes in, so I'll show that on the next slide. Basically, so what we did is we studied, so I did 100 of these kind of systems. So I looked at a sample of 100 systems that had gotten stuck with some form of domain walls that span the entire lattice. So they were going nowhere, and I made sure that all of them were going nowhere. And then we subjected them to an external influence for various amounts of times and variant magnitudes. So this is A related to AC squared, and then, or A squared over AC squared. And the 100-second simulation I showed you before is about 3 months if you actually translate, because you can translate time to a physical time. So these are the time scales for it. And you can see if you have really low magnitude events, so this is where I'm talking about, like if you run the simulation at even lower than this AC, it doesn't affect the system. You can already see that it's really like less than 10%. So actually, let me tell you what this represents first to begin with. So the actual value of the bar are how many systems were solved by this mechanism. So basically, they had domains to form initially, and then we subjected them to an external environment, and then they eventually, after that interaction, evolved toward homochirality. So the entire lattice had one chirality over it. So that's what the bars are for that. So for very low magnitudes of the external environment, you don't really get anything. So it's not really till if you have long duration events, so that's like the green bar in back, which is about 15 months. Even as you start to approach the critical value, you can start to actually have significant systems evolving toward homochirality after the external influence. And then for even larger values and larger times, you get a pretty good percentage that are actually solved by this mechanism. And then at shorter times, it requires higher temperatures, which is intuitively, or, larger impacts, which is intuitively obvious, I think. So you can kind of see a trend here about how they're influencing.
You need larger, yes.
Larger or
effects, so-
longer. So longer events can work with lower magnitude, lower magnitude, and then if you have short events, you really need the higher magnitude. It needs to be pretty much above the critical value in order to get any kind of significant number of systems evolving.
That's sort of, the bifurcation diagram was exactly in the other way around. I mean,
Right. So the critical the equilibrium values in the bifurcation diagram were found more in the terms of like a phase diagram. So you start
Okay.
with a homochiral solution and you figure out what the stable point of that system is under a certain magnitude environmental influence.
so if you go, yeah, right. So if you go below this 0.65 now again, then you're always up at 1, right?
Well, okay, so this is not, this value here is A over AC squared.
Oh, I see.
So this is 96% of that 0.65, right?
Yes, uh-huh.
So the axis here is labeled differently. I probably should.
But then below 1 you should be bifurcating all the time, I thought.
No. Above 1 you should be bifurcating all the time. Because it's above the, here, I'll show you.
But A is a noise, I thought.
It is the noise, right.
Noise
So if the
disturbance.
noise is really large, you should be bifurcating all the time, right?
Oh, because otherwise it gets stuck, you mean, yes.
Right. So if you go back, sorry. Is there a key field? Here, right? So if A is above, so this is like 0.65 squared.
Yeah.
If A is above that, you only have, that's when chirality is destroyed and you get racemic solutions. So what that last graph is saying in that case is that,
I think you're simplifying, yeah. You're also surprised.
right, so what this is saying is that entire domain network, the entire system was reset. So this
Yeah.
kind of, like, above the critical value, basically you're kind of almost starting from random initial conditions again. It basically resets the system. So this is almost like a measure of, it doesn't reset it entirely because you still have some remnants of the domain network depending on how long you're,
I think I understand what you mean, yeah. So if you go back
Yeah.
to the previous picture, that was simply
This
just,
picture is an equilibrium one.
yeah.
Yes.
This is the effect of the
That's the
short
stability.
arc pulse.
I mean, it's not even, right. So it doesn't really take into, this diagram doesn't take into account the possibility of,
Well,
That's the
okay,
thing
so
going getting
I
stuck.
think I know what,
This is a steady state. That's assuming you've got the noise on all the time.
right, yeah, that's the
Whereas
noise
this
on
is-
permanently.
This is a short pulse of that
Right.
noise.
So if you remember from the movie,
Uh-huh.
the noise was turned off, and then the domain network started evolving again.
Mhm.
So this is after noise is turned off, domain network evolves, and then it gets to its equilibrium value now. So that's just normal diffusive evolution after the noise. And then what percentage of those systems end up with one chirality over the entire lattice?
If you've got large noise, you'll effectively just start the system again from some sort of non-solution.
Right.
Whereas if you're far off on the left-hand side, the noise is just...
It doesn't affect anything.
So
Right.
if you were in a racemic state, you switch the noise on, you still be in a racemic state. If you were in a homochiral state, switching the noise on, the noise is too small to actually do anything, so you stay in the homochiral state. Compatible state where you've got patterns of homochiral.
Let me show this other picture again, this bifurcation, because then at least I understand still.
Right. So these values you have to understand are while the noise is still occurring. So this is the
Yeah.
equilibrium value in that turbulent environment.
Right.
Right.
So if the noise is strong, you clearly don't, during the time when the noise is on, you don't get anything, of course.
Right. So,
And so
Yeah.
noise is weak, and it always works. It never actually gets stuck, you say, even for weak noise.
no,
Yes, I mean,
for
the
weak
concept is-
noise, you can get domains.
Yeah, but then that's somehow not reflected in this diagram.
Well, these values, I'm not, well, this diagram started from it didn't start from racemic initial conditions. It started from a homochiral system, so you're not going to get domains to begin with. Well, these areas are actually the ones that would have domains, I guess, because they're partially chiral, right? So this has like a chirality of, say, 0.4 here, so that means half the lattices are, say, well, give or take half, and half is the left-handed phase. So you could have domains in this region. But basically,
But if you're at 0,
0 you have 1, right?
then the whole thing can get stuck. Many times, and sometimes.
Right, for low
So
noise.
there's a high probability of not reaching 1,
Right.
which is not, and you have high abundance.
Well, so this is what this is saying. It's saying if you have really low noise, whatever your chirality was before the noise was, well, that's not really right. It's not really affecting the system here because you already started with the chirality equals 1, so the low noise doesn't do anything to it. Whatever your evolution.
You start with 1?
Yeah, you start with 1. So all these simulations were started with everything equal to 1.
Yeah, then of course.
Right. So it's not really affecting the system
Yes,
now.
and then in the next picture you start with 0, right? Perhaps. Not this one,
Right. So originally these started with 0, and then they got stuck somewhere in here. And then you turn on the noise
Yes.
or the environment for 100 seconds, and then you see what happens.
Mhm.
So that particular plot is cutting it off here after one event.
Right.
So you can see that most of them will end up, because this is like a non-zero DABT, they'll end up at plus or minus 1.
Mhm.
And that's what that last graph is counting,
Mhm. Okay.
right? So,
Yeah, but maybe in this diagram,
right.
what is also important is not also the intensity of the noise, but the time.
Right,
it's
the
applied,
duration,
actually.
right. So there's two relevant
Mhm.
parameters here. One is the time and one is the actual magnitude of the duration of the event. Right. Okay.
Mhm.
So you can see, and then you can imagine multiple events. After multiple events, most of your systems are going to be one chirality or the other. And so the thing that's kind of obvious about this model is that it implies that the chirality is random. And so that's kind of where we draw our conclusions. So basically, our conclusion is that obviously chirality responded to environmental influences in the early Earth. And so if we actually studied extraterrestrial chirality, we should find it's racemic on average, because you have equal opportunity to go right or left.
Okay, thank you.
Any other questions?
Actually, well, it's not really a question, but actually, the kind of simulations in special, we might be some simulation that I've done. And okay, actually, when I've done this simulation into two-dimensional, it was some different kind of systems, but I never observed this kind of two domains that were stable. And I was quite wondering why, because, and I saw that in literature, discussed this also, so you have your simulation, but also I think that Hochberg, you know the papers of Hochberg?
Right.
And it also the same kind of systems with two
Right.
domains.
Well, anytime you have that kind of potential that has a domain wall,
Yeah.
anytime you have spatial distribution, or has a double well, anytime you have spatial distribution, you're going to have domain walls.
Yes, but I never observed the stability of two domains. And actually what I have in my systems, I have intrinsically always some kind of continuous noise.
Right.
So it's and I think it should be interesting to see that, because I think that in my systems, typically my systems were just a simulation of the crystallization growth of the crystals. So that is, even if you start with something that is only air, you have you always have some new crystals that are coming on the surface, and the surface is going like that. And I'm just looking at the surface. And I have not perfect selection. So even if you have only L, you may sometimes have a D that comes on the surface, and from this seed you have another D that is growing, etc. So it's never a perfect, even if you just remain like that, you have always some kind of fluctuations.
Right.
And in this case, it's interesting just to compare with that, because I think that in something like, I think that I have some kinds of, I just allow to go between the two, not adding some energy, but just because I have just add the stochastic fluctuations,
Right.
and sometimes just randomly I allow one place just to switch to
Right.
the other one. And just these statistic fluctuations is just sufficient to forbid this domain stability.
Right.
It should be interesting just to see, yes, to
So
compare that.
So you're talking about cellular automata simulations.
Yeah, I didn't intend it to be cellular automata, it's just after what that it looked like.
But that's, I think, important to say because we have one and the same model or idea,
Yeah.
and in one case one represents this with a deterministic equation plus a noise term or without a noise term,
Right.
Yeah.
and in the other case one has a completely stochastic.
Yeah, it's totally stochastic
Right.
actually. It's only
Yeah.
governed by.
Which is
Totally
using
Monte
the cellular
Carlo.
automata approach, where you do
Yeah.
have a diffusion term, right?
No, but I think it's a little as if there was some diffusion because exactly what happens.
So you're going to have to put
It's
that's not the same because the only way that your
yes,
deterministic model
it comes down to
is
the
way to
same.
extend it is because there's a diffusion term. That's the
Right,
only term
right.
that actually makes this.
Yes, but in my system, what is that? Okay, you have this the surface of the crystals, stuff for adding on top, etc., etc., etc. And so, if you have only, okay, if you have a L that comes there, then you will have new L that will be closed, etc. So you have some kind of diffusion, just because one L will force his neighbor to be L, etc., etc., etc. The particles by themselves are not moving, but they're propagating their chirality to their neighbors. So you have some kinds of diffusion. It's not exactly the same model of the basis of the model, but I think that if we look more close to the equations that describe the evolution, we will see this kind of diffusion of chirality. Well, actually, I really see exactly the same behavior with these zones that are growing like that. You have very random distribution and these kinds of patterns of growing, etc., etc. But because I have on top of that some continuously noise, some spots that appearing there and there and there, that separation of in between the domain can't remain very strict and very. You always have some fluctuation, and so it's never stable actually. It's similar.
But, if you, the whole thing, I think, can only then depend on the relative importance of the noise to the diffusion, and of course there's a time scale for the instability as well.
Yeah.
So this you need to adjust such that the models are comparable.
Yeah, it's not exactly the same model, of course, but I think that we there
That's
is a very strong link between these two approaches,
Right.
and I think it would be interesting to have exactly this kind of. I don't know if it's easy to deal and to adapt a totally stochastic approach to this kind of model, totally stochastic way to have really just to start with a fixed number of molecules and to have a probability of molecules to react. And I don't know how you do that to cut maybe your system in several cells, and you also have a probability that one molecule comes from one cell to another, or this kind of stuff. If you do that, would it work? Just not to put these equations of diffusion, but just have a stochastic diffusion. Is it possible to perform this kind of simulation? Because I think that maybe in this kind of system, adding some more noise maybe wouldn't be necessary. Maybe just the stochasticity of the system would be able just to destroy the stability of phases. And I don't know how this can be computed, if it's
Can you
possible.
maybe show us your A equation again?
Yeah.
Yes, that was. No?
Actually, you want it with the stochastic term on there too, maybe.
Maybe even this. Yes,
Yeah.
right. Okay, so I think the essential physics you would get already by just having. Let me think now. If you do the linear stability analysis, this gives it. This whole thing, I think, if you linearize, this gives A simply. So the growth rate is 1. So if you look at the linear growth rate at one point, you have a growth rate of 2 minus 1, which is 1. So, and then you have this type of term,
Yeah.
And such a system is called the Fisher equation.
Yes.
In the very simplest case. Now I think the question, maybe I should erase that then. And the simplest, and now the question would be, what happens if you want to solve the Fisher equation with the cellular automata approach?
Yeah.
Does it work or does it not work? Of course it should work. Yeah.
Yeah, it should work, but
So if the simplest system then would be
yeah.
the Fisher equation, which means, yes, use the letter u. U dot is equal to lambda u, and there would be a stabilizing term in the Fisher equation, which is 1 minus u, and then plus u double prime, and there would be a diffusion coefficient kappa.
Yeah.
And that's your equation. And now you can solve this with the cellular automata approach. How would you do this? In a one-dimensional mesh. And of course, the solution to this is that we have a front which propagates in this direction with a constant speed. And the speed, by the way, of course, the front speed is equal to the square of the, yes, it's equal to kappa divided by lambda.
Okay, what I was thinking about is maybe just
And
even maybe
over
about
2, right?
It's a root of
Over 2?
square root of there's a square root series.
Maybe, yeah.
I mean that's well maybe just what I was thinking okay, if you have in one dimension in each place you have a number of x compounds and that to say that there is a possibility of diffusion, so you have one probability that one x goes from there to there, one probability that this compound comes from there to there, and this probability is proportional to the number of elements inside. If you just do that, you find back the diffusion equation, I think. If you just describe the system like that, this is equivalent to the diffusion.
Yes, so can you maybe repeat it again? You have a certain probability of...
Yes, you have n molecules inside. Okay? And from that, if you say that you have one given probability that one molecule swaps there to there,
Yes.
and the same probability that one molecule could swap from there to there.
Yes.
And of course, you have that for all the cells. This is exactly equivalent to the diffusion.
I think it's
It's
the...
a diffusion, but it doesn't give you the nonlinear interaction.
Yeah, but if you have that, and then you have the reaction inside the cells,
I mean...
maybe it would be similar. I think it would be similar to the system.
Yeah, so first the diffusion thing, I think you would have a relative probability also of one half staying inside, maybe. Can you do?
Yeah.
Is that maybe not required?
Not.
Depends how you scale the space.
Because the diffusion operator really corresponds to an averaging. In exactly this fashion if you do it second order.
Yes, but so to the way to describe that without averaging, just and with that, and
So
then
now
you
you
add the probability of reaction. If you have
And the nonlinearity is of course trivial because that's just valid at every point.
yeah, and maybe just describing, adding this. It would be just a different approach that would be equivalent. It would be interesting to see that is just this stochasticity sufficient to destroy the stability. I don't know, but if my previous system that I modeled is equivalent to this one, I'm not sure of it because it's not exactly diffusion that I'm describing in my crystal stuff. But if it is equivalent, I think that the stochasticity would be sufficient.
So, so the initial condition would be one where we have 1 on the one side and exactly 0 on the other, right? Exactly 0. And that means if you turn on your instability, because this one is really exactly 0, it will never grow.
Yeah.
And this, of course, will grow to infinity.
Why?
Because it's not to infinity, to 1, of course.
It stays at 1.
Yeah. So it stays at 1.
Yes, but
So, but if it's less than 1, it will grow to 1.
yeah, it goes to 1. Yes.
This is 1. And then, but the front will not propagate. There will be no propagation because you don't have diffusion.
Yes, but then you add the diffusion like that.
And then you add the diffusion, yes?
If you add, it would be that, okay, you have some probability that it comes,
Yes.
and then it will diffuse in this direction.
And then we should have a front speed that goes with the square root of the noise amplitude.
Yeah. What do you mean by noise amplitude?
Because the noise does, this is what is done by noise, the diffusion.
Oh, the diffusion.
Yeah, everything is just
What do you mean everything?
is performed by random events. So
But this is what I mean. Is there anything else in this? You said
the reactions themselves are also performed by random steps.
Okay, but so he's saying here's actually also similar.
I think that actually if doing that randomly, it wouldn't stay at zero because maybe okay one random event will be up there and so you will be something like that. So maybe actually even if you start from zero, it will go to 1 or minus 1. That is if maybe actually it will be you have some positive, some negative, and what will be interesting is at one point maybe we have plus 1 and minus 1. How will behave this front actually? Is the stochasticity will be sufficient to destroy it? It's really the question. Is the stochasticity sufficient to destroy this? Or will we need inputting this kind of randomizing stuff so that we destroy
So
the
first
front?
of all, in the Fisher equation, only positive solutions are permitted.
Yeah.
So if you want something that's plus or minus, you have to go back to this equation again.
Yeah, it's different because the Fisher equation has a first speed that moves, whereas this
Yes,
equation
correct.
the domain's
Okay.
stationary.
So therefore I think this is a very good test, yeah. So we want to use this then instead. And then of course it means this is being replaced by this. It would also be lambda, I think, outside. It's
just one minus u
outside.
squared,
I think,
isn't it?
yes, okay. So there would also be lambda outside, which is u lambda 0. And then of course it has twice, let's write here u. Or let's even write,
Just write instead of having 1 minus u on the equation first,
Sorry,
1 minus
yes.
u squared.
So we have 1 plus a squared, and we have 2 minus 1, which is 1 minus a squared. Yes, so that's in u, of course.
You don't need the 1 plus u squared, of course.
That's unimportant to me. Right. Yes.
And what that equation does is you get domains that are plus 1 and domains that are minus 1. And if you do similarly long enough, you
Yes.
Yeah.
so you get some sort of you get little bits which are plus 1, little bits which are minus 1. And these are basically stationary, but they're
Yeah.
moving very, very, very slowly.
But I think that in one dimension anyway it will be always stationary because you
No,
direct
they're
something.
not.
No?
What happens is these very slowly move, and they move such that you
Yes,
find
but they have no reason to be moving more in one direction than the
they
other.
do.
You think?
Yeah,
Right.
because they interact with each other.
Okay.
Because they're not. It's not exactly a square.
Yeah,
wave.
okay, maybe
They
yes.
have slight exponential tails, and the tails
Also,
interact.
maybe even in first
And they
dimension it can
interact.
work.
They interact such that
Okay,
the smallest
okay.
one decays first. So if you waited a bit, if you waited long enough,
Okay.
the smallest one will disappear, and then
Yeah.
you'll get that.
You could still
And
end
then
up
the
with
next
one
smallest
less
one will
one.
disappear. and you get that.
Oh, it's really working. Yeah.
But depending on whether it's even or odd, you could still end up with one domain, like one kink in your solution. If you
Yeah,
don't
depending on your
cancel.
boundary conditions. Yeah, if your boundary condition overrules that,
Right.
you end up with one kink.
Yeah.
But it's always the smallest one that
Right.
gets an eye. That's it. And you have to wait for that to come such a long time.
In your case, it could be minus 1, sorry.
Yeah.
Yes. I'm still surprised. I thought they should get stuck. Exactly. So
For that one, it depends on the boundary conditions, I think.
boundary conditions, but they are a priori, for example.
They
That's
they
true.
interact, they're not. So you've got the tail of one meeting with the tail of the other. It's a very, very weak interaction. So. And you can work out the distribution of lengths and how it evolves over time and solve some of them.
But
Yeah, but
I see.
it's similar to this banded problem, I think. In this banded problem, it's stable.
So I think
If you've got vertical bands, it's a 1D problem, so it's just exactly the same approach.
Yeah, but this is stable.
no, I think what he's saying is this.
It-
No, it's not.
It's not. It's really not stable. I think that also lots of paper, if you have really this approach that say that this is stable, so I
So
don't.
the
But I
reason-
think in
the
1D,
reason
if
why
it's
it's stable
periodic boundary conditions,
is
it's not
because
stable.
this is not the solution. So if the solution was a single kink,
Yeah.
it would be
Yeah,
stable.
if you have just an infinite minus
So
1 and
Right.
an infinite plus 1.
So the-
Right, that's stable.
So the-
Again, if
Yeah.
I think this is the case, maybe that
That's
is
So the
maybe.
degree of interaction then depends on the width.
Yeah.
If the width is finite,
Mm.
if the width is not if the width is very small, there will be a fast interaction, and if it's bigger and bigger, it will be progressively harder and harder
Yes.
to let it move. Okay, right. So I think we should still look quantitatively at this equation and see whether. Uh-huh.
But
That's not the right thing, then, of course.
it's one of these metastable things that when you make the simulation so slow that you assume
Yeah.
it's reached equilibrium and you just
Yeah, maybe it's not that good. I thought that this kind of system, even theoretically, they should be stable because there was no reason to wait to
No,
go
there is
in
a
one
reason.
direction rather than in other direction.
But there is a reason.
As long as because I thought that what
No,
is
wait.
changing the front is maybe just the curvature of the stuff.
Yeah, but no,
But
wait.
when it's a right line, even if two right lines are close.
I understand what you mean.
Okay.
I understand what you mean. But the point is, there is a finite width. This is a minimum here.
Yeah.
Finite width, and therefore there's a certain advantage in closing this gap
Mhm.
relative to moving to there. I mean, you could equally well move
Yeah.
to there.
Actually, I understand that.
But then there would not be no.
Yeah. So I mean, okay, if it's okay.
But you,
If
you wouldn't do
it's
that.
actually something like that, it can make the
Yeah,
difference.
yeah, yeah.
But
Exactly.
if it's very short, it will be something like that.
Yes, that's right. That's what it is. It's really.
Okay, and
Well, they can have some width
so and
associated.
if it's very sharp, maybe this is very slow and it looks like an infinite time of diffusion. Okay, see.
The only case which isn't really in equilibrium is if you have periodic boundary conditions and the widths are exactly the same, because that's
Yeah.
and you've got the same
Yes.
tension in each.
This will be stable, but
Well,
not really stable because if you have a little fluctuation in one, it will destroy, and so it will.
It will be stationary, you mean?
It can be stationary,
Yeah.
but it won't be stable.
Yeah. Yeah. I see.
So, yeah, okay, so maybe we should think whether we could put the general, either the Fisher equation and or the generalization of the Fisher equation to the plus-minus situation. The Fisher equation, of course, is something like the spread of a disease, the black death through Europe. That's described by this. And so the other equation is having a black death and a white death. So we have the black death spreading through Europe, and there's also a white death. And once the white death starts to compete with the black death, it gets stuck. But otherwise, it doesn't get stuck. Both the white death and the black death, they can both propagate.
Oh boy, then you're in
With
trouble.
this speed, of course, right?
Yeah.
So that's interesting. So I think maybe you need the S equation as well. So I'm
Well,
not sure it's the S
it really
equation.
the S equation evolves so quickly to one that it doesn't affect the system. that
Yeah, but
much.
on the boundary, is it 0? Can you show us again? The full system, maybe? Do you see what I mean?
Yeah.
The full system of equations is with S and A, symmetric and antisymmetric.
Right.
But really,
That's the other one.
diffusion
Previous.
previous as well.
The full equation, further back. Yeah.
They have different numbers and different values.
The what?
The The K in the S equation should be different to the K in the A equation. So you can assume that the K S diffuses, so it reaches its plus or minus 1.
So S is strictly 1.
S,
Okay.
S,
But,
S has to be positive, doesn't it? S can't be
Right.
negative, so S would be 4.
yeah. But but right. And that's no, I understand. So if you want to be healthy anywhere and you don't have either black or white death, then you do need the S equation. Because the S equation tells you that no matter what, you will be at some. If you wait, if you're healthy, it's okay. Then S is 0. But sooner or later, you will become either black death or white death. And so maybe we better do this with the S equation. But I think it's interesting to just solve the Fisher equation first and try and do this with the cellular automatic. Anyway, so maybe this is we should think and go for lunch, or what should we do?
Yeah, maybe it's better not to go too late.
Yeah.
Avoid the queue. And to find a table.
Okay, so thanks,
Yeah.
Sarah.